Good morning, everybody.
Good morning.
All right, let's get word of the day done. There you go. That's the word of the day today, which is barycenter. Doesn't have anything to do with people called Barry. I had an uncle called Barry. It's all about the center of mass around which two objects, typically a planet and a moon or a star and a planet, rotate. It's going to be super important for one of the things that we're going to be looking at today. So let's get some stuff up. Make sure I get my chat. Don't want to miss any, don't do that. Comments. There we go. Okay, so today we're heading back into the wilds of astronomy. Take that equation off there. I was staring at that until my eyes started bleeding for a little bit. We are going to be looking at exoplanets, right? So this is the I don't know, the big holy grail, I guess, right, of astrobiology is trying to find a planet or planets around other stars which have environments that are suitable for life as we know it from our own very limited sample size. And, you know, I guess you could take two views. One is that our efforts are best spent here in our solar system, right? Because it's closer, it's easier to get to. We can actually go see if there's life in these places on these moons out further out, or even on Mars, right? But the problem is none of those places are super ideal in terms of environments. They all have their own challenges, right? They're all extreme environments from one degree or another. And so the flip side of that argument is, well, there are an awful lot of planets out there. They actually think that there could be up to 20 billion planets orbiting stars in the star's habitable zone. Just think about that, 20 billion planets that could potentially host life, right? It's a pretty stunning number. We obviously don't know that there's that many, but there's just an extrapolation. So the other perspective is that, well, there are lots of planets out there that are in kind of similar conditions to Earth, right? They orbit their star in the star's habitable zone like we do. And I'll be showing you some of these later, probably on Monday. There's just a lot of cool stuff out there. It's super, super fun. And it's like science nerd fest to the max, basically, sci-fi stuff. There are also plenty of Earth-shaped and sized planets out there. Obviously, there's a bias in how we detect them, so it's a little harder to find places just like Earth for various reasons. But there are lots and lots of potential candidates out there. And with improvements in astronomy, and particularly those very big ground-based telescopes like the Very Large Telescope down in Chile and the soon-to-be extremely large telescope, I'm not sure, can't remember where that's going to be, as well as the James Webb Space Telescope that's going to go up, I think, in the next year or two, which is really, really exciting. That's essentially the replacement for the Hubble telescope, which, you know, a huge amount of our understanding of the cosmos comes from the Hubble. Anyway, we can actually start looking at the atmospheres in some detail of those exoplanets, right? And that's super, super exciting. So essentially what I'm going to be doing for the rest of the semester, really. There's going to be a little bit of sci-fi stuff at the end because you can't really talk about discovering exoplanets without talking about how we're going to get there, right? So that's probably going to be the last formal lecture, and that's just going to be a kind of an indulgence on my part, really. But the rest of the lectures are really going to be about, you know, how do we find these things? And that's really what today it's going to be about. What have we found? Right, that's the other big thing, right? And so on Monday we'll be looking at some kind of key discoveries, right? The most exciting ones. There's one called Tatooine, right, after the planet that Luke Skywalker grew up on in Star Wars, with its binary star system. So there is an exoplanet circling a binary star system, which is pretty crazy. All kinds of stuff. That actually, they all seem to refer to places that were in Star Wars, to be honest. There's Ice World of Hoth, right? There's another one. Things like that. So they're super, super cool places. And then to finish up the exoplanet thing, we're going to be looking at Proxima b, right, which is our closest exoplanet. It's about 4 light years away, which is a hop, skip, and a jump in galactic terms. Most of the ones discovered by the Kepler Space Telescope are 300 to 1,000 light years away, or 3,000 light years away. Not that it really makes much difference, right? A light year is still a bloody long way. It's not going to make much difference whether it's 1 or 1,000. And also another solar system, right, which is actually shown here. This is the TRAPPIST-1 system, and it is we mentioned it briefly a while ago when we were talking about Jupiter and the Galilean moons. But this is a solar system of, I think, 7 planets. Yeah, I think it's 7. Can't remember the exact number off the top of my head. Orbiting a small red dwarf, so a smaller, pardon me, cooler, redder sun than our own, right? So kind of at the small and inferior end of the main sequence, I guess. And we'll talk about some of the stuff around that, and that's just a really crazy place. Anyway, so stop me if you have any questions. There is some math involved, but yeah, I kind of like wander away from that as much as possible. There is actually an equation in here which I forgot was there, so don't panic when you see that, because I don't understand what it means really, to be honest. So yeah. Anyway. Oh, and also sorry about not doing the audio walkthrough for this. Hopefully that won't affect your understanding.
All is forgiven.
Oh, good. Yeah, it took me a long time to get this together yesterday, so I just kind of ran out of time and energy, and it wouldn't have been much point posting an audio walkthrough at like midnight last night because no one would be listening to it. Anyway, so this is a series of images from the Kepler Space Telescope. So there's basically been a progression of telescopes launched over the last, oh God, I guess like 25 years now, with ever increasing capacities and kind of more and more refined missions. And obviously the Hubble was the first one. And I actually remember seeing pictures from that when I went to the European Space Agency spaceport in Guyana, French Guyana, in South Africa back in 2000. And I remember looking at those pictures of, the Horsehead Nebula and thinking it's just amazing. And so the Kepler is, I think, like the 3rd generation, 4th generation perhaps of those space telescopes. And essentially its mission was to have a very, very fine kind of pencil beam search of one particular part of the Milky Way, right? We're not worrying about other galaxies here. We're just kind of looking within our own galaxy. Right? There are loads of other galaxies flying around all over the place. We're just worried about our own right now because that's more than big enough to start with. And so Kepler basically fixed its gaze for months at a time on one particular small segment of the Milky Way and watched for planets moving in front of their sun. And essentially, and we'll talk about that as a method in a little bit, these are pictures of that. I don't know whether they're actual real pictures. I don't think so. I think they're more visualizations based on luminosity size and various other parameters. There's an awful lot of math involved in this, which is why I'm not an astronomer. But essentially, you can see that you get all kinds of stars and all sizes of planets, right? You get some big ones, you get some real big ones, like down here. You know, that planet is a pretty large fraction of the size of its star. Oops, get rid of that. And so there are thousands and thousands of exoplanets already been discovered. I think the current count is something like 4,100 confirmed exoplanets, and nearly 700 of those are multiple planet systems, right? So actual solar systems. And you can also see, obviously, there's this big range in size of the star. Typically, you don't find many kind of super bright stars, right? So these, I think they're called O-class stars, or B-class stars, maybe. I'm not very familiar with the sequence. They're typically G-class or smaller. Don't know exactly what this one is, right? For a bunch of different reasons, which we'll get into in a little bit. So essentially, there are lots of different ways you can find exoplanets, and some of them more successful than others. And also, they have their own inherent biases. And that's something that's really important to keep in mind when we're talking about looking for exoplanets. There is no perfect method of finding them. Each method has its own issues, right, in terms of what kind of planets it finds, around what types of stars, how close those planets are, what type of properties those planets have, etc., etc., or even ability to even detect that planet, right? And so whatever the number that we've found so far is almost certainly a massive undercount of how many exoplanets are actually out there. So this is a graph that I filched from Wikipedia, and really annoyingly small labels on the axes. But essentially, these are the different methods by which exoplanets have been discovered, and it started around 1992 was the first one, where a planet, I don't know how they did this, was discovered around a binary pulsar system. So pulsars are rotating neutron stars that emit radiation from their poles, and there's a planet orbiting two of those. Must be a really weird place. Anyway, the main colors here are green is the transit method, which is what Kepler uses and tests now as well. And the red is radial velocity. And so we'll spend probably more time talking about those two because they're really the most important methods. But there are some other cool examples in the other ones too. And so there are more than these. These are just the ones that I wanted to talk about. Not really going to talk about transit time and variation, but very much because that's really more about multiple planets. That's more about solar systems. And that essentially is how one planet affects the transit time of another planet based on its speeding up or slowing down its orbit around the star. Pardon me. Sorry, I just had my breakfast. It's not going down too well. So the two main ones are radial velocity and transit photometry. Now there's going to be a little bit of physics going on here, right? And some of this is a little bit tricky to get. So if you don't understand it, just stop me and ask. We can go over in this lecture into Monday if necessary. I've been thinking about this stuff for many, many years, so it kind of falls somewhat naturally to me, just through being familiar with it, familiarity, right? So radial velocity is a funky one. Transit photometry is really easy to get, but radial velocity is really, really funky. And so it's based on, I'll just go and try and teach it. Anyway, I've got to put this up as an actual animation because this, is Paul here? Paul, you here? There's Finger's phone. I don't know who that is.
It's Jimmy.
Oh.
Yeah, I'm outside working out on my phone.
Well, that must be a very big phone, Jimmy, for you to work out on it. Or a strong one. Oh, well, I actually, let's see, is slideshow going to work? Look at that. Isn't that awesome? I hope you're sitting down. I'm not standing up right now. Can you all see that? Those doing their thing?
Yeah, we can see it rotating.
They're super cool. I could stare at these for ages. Anyway, essentially, the red plus sign in the middle is what's called a barycenter, right? So this is the object around which two things rotate, and the easiest one to think about is the one at the top right. You know, you have two equal mass objects. Their shared center of rotation will be equally spaced between them, right? That makes a lot more. That makes plenty of sense. Now, this one over here on the top left is super funky. I just put it there because it looks really cool, basically.
Isn't that like literally how elements work? The left side?
Yeah.
Imagine the planets are the electrons and the plus is the protons or the nucleus.
I don't know, Jimmy, to be honest.
Never mind.
It's a good answer. I'll go, yeah, sure. I'm totally down with that. Anyway, there we go back in. Now, the one that I really want you to look at, which is more important to what we're talking about, is this one at the bottom, right? And so this is actually a fairly good representation of a slight exaggeration, really, of the Earth and the Moon, right? And it's the sizes and the relative masses are similar. So essentially, the Earth, due to the pull of the Moon rotating around it, doesn't rotate exactly around at one point. It actually kind of prescribes a small orbit of its own, right? Because the shared mass, the shared center of gravity is actually inside the Earth, but it's not in the center of the Earth, right? So the Earth kind of wobbles kind of a little bit around that barycenter as the Moon rotates or orbits around the Earth, right?
Is that why the plus is like kind of on the edge of the planet? It's because it's rotating around that outside point instead of the middle?
Yeah, so if you actually look at it, the center point of the large object in the middle is following that very small red circle, right? That you can only see part of it as the planet rotates. Can you see that? So there's a big red circle which the Moon follows around here. There's a small red circle. Yeah, so essentially the this is hard to describe with just hands, right? But basically the Earth is doing this, even as it's spinning around its internal axis, right? In space, it's actually kind of doing this. Don't know if you can see that, because I can't see what I'm. There we go. Let's put me back up here so I can actually see what motions I'm making. There you go. Oh yeah, you couldn't see that because my webcam wasn't pointing in the right direction. So the Earth is doing this as the Moon is going around it, like so. But because the mass of the Earth is so much greater than the mass of the moon, that shared center of gravity is going to be within the Earth. It just means that the Earth doesn't do this. It kind of does that as it rotates around itself. Does that make sense? Hopefully. Maybe.
Definitely.
Cool. Awesome. Now the funky thing is, and I did actually mention this, let's get that off there because it's kind of making my eyeballs start kind of rotate in different directions. Yeah, get back there. We talked about this ages ago. I don't know if you remember, but Pluto and its moon Charon, the center of mass is actually, because they're relatively similar in size. Charon is about half the diameter of Pluto, something like that, about a quarter or an eighth of its mass, but much closer than the moon and the Earth are. So Pluto actually prescribes an orbit around that center, right? And that center is outside of Pluto. So Pluto actually orbits around like not an imaginary point, but a point in space.
In between.
Yeah, exactly. Which is pretty funky. And this
is that. Oh, go ahead.
No, go on.
I was gonna say, is that because they're tidal locked? Like Pluto isn't actually rotating as it goes around that axis point?
Tidally locked is more due to the fact that the tidal locking occurs because of how close they are. They basically slow each other's rotation to the point where their rotation relative to each other is fixed.
So they just keep facing each other instead of rotating around another rotating point.
That's right. So what you'll tend to see in planets that are close to their star is that they will become, or even moons actually, if the difference is large enough, they will become tidally locked to them. So moon is tidally locked to the Earth, right? We only ever see the same face of the moon. But the difference in mass between them is such that the moon hasn't slowed the Earth's orbital rotation around its axis enough to make the Earth tidally locked. But the moon is actually slowing the Earth's rotation around its axis. It will take, I think,
eventually we might get there.
We will. I think it's about like 2 billion years from now. So,
Yikes.
Don't hold your breath kind of thing. So that will happen with the Earth. It just hasn't happened yet because the differences in mass are so large. This is more because their masses are quite similar and they're quite close together. And so because their masses, the ratio in masses is relatively small, the center of mass is more between them. Actually, if we go up to here, right, this one on the top right is a great example. The ratio of mass here is 1:1. So the center of mass will be exactly in between those two objects. The ratio of mass here, I think, it's about 1:8. I can't remember exactly off the top of my head. And so actually that kind of makes sense because the center of mass is about 1/8 of the distance from Pluto to Charon, right? But because Pluto is relatively small, that 1/8 of the distance is actually outside of it. Whereas the Earth, the ratio of mass is much larger, and Earth is much larger, so the center of mass is actually within the Earth. I think that's probably the best I can do. I think that makes sense to me. Maybe.
Yeah, it makes sense.
Yeah. Okay. Cool. Okay, so this is really, really important because essentially, if that object, right, so if it's not Pluto or Earth, but it's a star, what you now have is that star is essentially prescribing a small orbit of its own, right? And so relative to us, because the planet that's orbiting it has created that barycenter, right, which is probably still within the star, but the star is not spinning on its axis in space. It's spinning on its axis while making a small orbit. And what that means is that when we observe that star is, at least if the orbit is that it's prescribing is edge on, that's pretty critical. That star is kind of, sorry, gotta keep an eye on where my webcam's pointing. That star is moving away and coming closer, moving away and coming closer, moving away and coming closer in a periodic manner, right? Whereas normally a star just on its own will stay fixed in space, right? It's not going to prescribe an orbit.
I imagine that has like a hellacious effect on seasons, huh?
Just trying to think. Yeah, it probably would actually. I don't know.
Every time it pulls away.
Yeah. Well, the thing is the distance. Hang on, let me just double check these again.
Yeah, maybe it depends on the size of the sun and how far it's actually moving back and forth.
Yeah, it's not huge. It's not like
Okay.
it's like zooming back and forth over millions of miles. But it is moving back and forth enough to change the wavelength of the light that we see from that star. And
That makes
so,
sense.
has anybody ever experienced the Doppler effect? You know, it's quite common with like sirens and stuff.
You mean where like it's coming from a different direction, but it bounces?
No, more that if you have a siren coming up behind you, it will be higher pitched until it reaches you, and then it goes lower pitched as it moves away from you.
Mm-hmm.
Yeah, I actually had that with a dog once. I call it the Doppler dog. It's riding along on my bike, and there was a dog leaning out of a car barking at me, and it was like ruff, 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 as it kind of went past, which I think is pretty cool. That's a very memorable moment in my life.
That's
Anyway,
awesome.
yeah, call it the Doppler dog. So if we're not to scale, if there is a star with, and there's always caveats here, if there's a star and it has a planet of sufficient mass, right? Because a really, really small planet far away from that star is not going to affect, it's not going to create a barycenter that's significantly different from the star's axis of rotation, right? So it has to be a star with a planet, obviously, because that's what we were looking for. Pardon me. The planet has to have sufficient mass to create an offset center of mass, right? A barycenter. And also, most likely, that star will need to be fairly close. Planet, sorry, will need to be fairly close to that star. And fourth, I've got enough fingers there. There we go. That solar system, that extraterrestrial solar system, will have to be somewhat edge on, right? So if you have, you know, your star in the middle and a planet orbiting around that, you're going to get some wobble of that star. That star is going to kind of, you know, basically do this right around in an point in space. But we're not going to see any change in light because we're just going to get the light coming straight at us from its, say, its north pole. So you have to basically change that to more in plane. And so now, that's kind of weird, right? Now you have that star is kind of going to be going back and forth a little bit towards and away from us. And so as it does, you'll be able to see basically a red and a blue shift in the light coming from that star. And that's essentially shown kind of here. And it very much depends on the relative position of the Earth or us looking at it as to what that shift will look like, right? But essentially, as the star is moving a little bit towards us, space-time gets compressed. And so the light coming from that star essentially gets compressed too. So it goes to a shorter wavelength, and that shifts it to the blue spectrum or the blue end of the spectrum, or higher frequency essentially, right? And so you can actually see that in this like schematic down here. And then as it kind of moves away from us, again, relative positioning as well, then that space-time stretches out. And so the light kind of crossing that space-time also gets stretched. And so the wavelength increases, and then it shifts to the red end of the spectrum. Yeah, Doppler dog was pretty cool. I've had a lot of, I also have the Doppler yokels as well, which shout, "Get off the fucking road," as they go past. It goes, "Get off the fucking road," as they go past on the car. I live an interesting life, what can I say? Anyway, and obviously as well, the distance and the kind of the angular separation matter too. So the further away they are, the relative distance in that wobble gets smaller and smaller and smaller. So the shift is going to get smaller and smaller and harder to detect. Right. So there's definitely issues with this method, and it's not a trivial one. Particularly the biggest issue, and this is one that the transit method suffers from, is that it will tend to pick up large planets, right? Because of the shifting of the barycenter, or creation of a barycenter, essentially, right? Which will cause that star to wobble, right, and create this change in observed spectra. And so if you actually record it, which one was this for? This is for Pegasus B. I'm not really sure. Does it have any notes down here that's useful? Yeah. 51 Pegasus B. You'd have to go look it up to see what star that is. But essentially, this is following from. This is mapping the radial velocity of that star based on its change in emission spectra. And so you can see that it kind of wobbles around its 0 point, essentially, right? So kind of down here, you'd expect the light to be shifted in one direction, and then it goes back to whatever wavelength it should be. And then as it goes up, it gets shifted kind of away in the other direction, right? So this actually shows you that this star is prescribing a small orbit, right? You can actually measure speed at which it prescribes that orbit by using this method. And the only way that that's going to be caused, obviously there's lots of math and kind of craziness involved, is by another massive object that is going to be in the same vicinity as that star. And it can't be another star, because if it was, it would be emitting light and we'd be able to see it. So obviously you get this with binary stars, right? They do the same thing, but you can see both of the stars. So you can rule it out being a star based on the fact that you can't actually see the other thing, typically. Does anybody have any questions about radial velocity? It's a little tricky. It's not too bad. Kind of makes sense if you think about it for a bit.
No, I'm good.
Anybody else? Happy to take questions.
So like pretty much if the planet is too small to like have the sun move even a little bit, we won't be able to detect it?
Correct.
Okay. Thank you.
And also, if the plane of the elliptical of that particular system is tilted too much, you also won't see it. Right? So if the planet is rotating around its star like so, like 90 degrees essentially, we're looking down from the north pole of the sun, right? We're not going to see any. You're not even going to be able to detect that planet. It has to be, I think, within about 15 degrees, give or take, of the elliptical, either above or below, to be able to detect a planet in this method. And obviously, the bigger the wobble, the more you're able to detect it out of plane. The smaller the wobble, the more it would have to be exactly edge on. Essentially, you're looking at a difference, and that difference is either going to be caused by something massive or by seeing it exactly edge on. Yeah, but there's definitely an awful lot of biases involved in these detection methods. It's just kind of inherent in it, unfortunately. Does anybody have any other questions? Cool, and that actually, Chiara gets back to I don't have any images up here of, I don't think I have any, hang on, what's this look like? Oh yeah, this is actually a fairly decent illustration of this issue. We're just kind of jumping around, it doesn't really matter too much. But essentially what you'll tend to find, right, so this is orbital period, right, so how long it takes for the planet to orbit around its parent star. And this is the mass of the planet, right? So this is us down here. As you can see, there are very few exoplanets detected down here. You can actually have some that the mass of the radius of the Earth, but their mass is going to be a lot higher, right? They're a lot denser. And what you tend to find a lot more of are large gas giant sized planets. So things like Jupiter, and actually much larger than Jupiter. There's the largest one is that's been discovered is 30 times the mass of Jupiter, right? And if you think about Jupiter and Saturn have well, like 90% of the mass of the solar system other than the star, right? So these freaking huge planets, right? They're actually so huge that they're not entirely sure if it's a planet or if it's a brown dwarf, right? So a star that didn't get big enough to ignite, right? And so this is a good image of the the bias, particularly with regards to size, right? You'll tend to see much larger planets than our own because of this. That's obviously a lot more of an issue with, so this is radial velocity, right? So this is the Doppler shift method. This is transit, right? So this is more biased towards things with small orbits, and we'll get into, or short orbital periods, right? And we'll get into why that's the case in a second. Humming. Okay. Okay, so the other method, which has actually been far more successful, but obviously also has its own issue, is what's called transit photometry. And so essentially this relies on, again, having a star and solar system, right, in plane with us. Because what you're looking for now is you're looking for a star, and then, hang on, let's do it the other way around. Haha, do like a model on my webcam, right? So, and then you're looking for a planet to basically come in front of that star. And then you're measuring a small drop in the light output of that star, right? And you can actually see that really nicely here. This is a tiny planet, right? So it causes a very small drop. But as the planet gets larger relative to the star, you see a larger drop in the light output of that star. And if you look at this, this is actually, this is from the SOHO satellite, which is Solar and Heliosphere Observatory. It's been looking at, actually, haha. You can actually see it in video. Check this out. Oh. Don't know why they have African drums playing to that. This is Venus going in front of our sun. So this is a Venus transit, right? And so if there was an alien civilization doing exactly this. Maybe there's an alien professor teaching astrobiology on, you know, some exoplanet somewhere, and they were watching our solar system edge on. Zoom, there it goes, pretty quick. They would potentially be able to observe exactly this, right? But Venus is a relatively small planet. Yeah, the sun is big. It's really, really big. The reason why it doesn't look big is because it's so far away. It's like one of those cows in Father Ted. You know, it's either a small cow close up or a large cow far away. The sun is definitely a large cow far away. And Mercury looks even more insignificant, right? Mercury is even tinier. And so, yeah, that's just that. You could spend hours on that on the Soho website looking at videos. It's just astonishing, right? Some of the stuff that they've produced from there is amazing. And so this is essentially what it looks like in kind of like snapshots, right? So if we were to observe the sun and the light output from the sun, we couldn't do it of our own sun because we're too close, right? We wouldn't be able to detect much of a difference. But if you're far enough away, then you can actually tell when Venus is transiting in front of the sun. And same for Jupiter, kind of less so because it's a lot further out. And so it just looks cool. I just think it's super neat. So this also has its own issues as well, right? And there's another transit. Let's see if I can find. Let's see. Yeah, I couldn't find it. I'll have to go and have a look at that again. I don't want you like trawling around in my browser history of Soho and stuff like that. Very dodgy. But anyway, there's another image of transit of Venus, and it's actually Venus's transit's a little bit below, obviously a different perspective, right, of the observer. And so it's a little bit below the sun. So if that were the case of a alien observer, you know, some light years away, they would never see that planet, right? Because it would never produce a drop in the output of our sun. And so transit method is actually, it's a very powerful method because you can do it en masse, right? It's very easy to scale up. And in fact, TESS, which is a mission that went up in 2018, is doing exactly that. It's Kepler was like a very focused pencil beam look at the galaxy. TESS is going to be surveying all of it, of the Milky Way, at least within, I think they're aiming for like 30 to 50 light years away, so relatively close. And so the big issues with transit photometry is the bias, right? And so obviously you're only going to see things which are edge on, right? Because the planet actually has to physically move in front of the sun for you to be able to detect it. The other thing, which is another bias, which is kind of makes sense when you think about it, is this one on the left here, right? So the blue is transit, right? Oh, hello, doggo. My teenage dog has come down from bed. Now it's just going to lie down on the couch instead. She's a pretty lazy ass dog, to be honest.
That's awesome.
Yeah.
It's like a family member.
Yeah, she is. I actually find her quite often sitting like that in front of my laptop, which is it's like she's
learning.
Yes, that's right. You funny creature. And so the transit method is biased towards short orbital periods because, oh, hang on, Pedro, I'll just get to your question in a second. Essentially, if you have a really, let's say you had a huge planet like Jupiter, right? Let's say we're observing our own solar system from a few light years away. I can't remember how long does Jupiter take to orbit the sun. I have to double check. Let's have a look. Dog, hang on. Stop that. Licking her bits on the couch. 12 years. There you go. So, let's go back here again. So if you were to see a transit of Jupiter, let's say, right, something equivalent to this, right? Now, obviously this is Venus, but let's say you saw a transit of Jupiter. Now, just one is not enough because suns fluctuate in their output a little bit anyway. Ours does, and red dwarfs do even more so. So you would have to wait another 12 years for that planet to transit back in front of that star again to confirm that finding, right? And probably you'd have to wait another 12 years just to double check to make sure it wasn't some weird funky thing going on. And so we don't have, pardon me, transit results for many planets that are far away from their stars. And so that's another fairly massive bias in terms of our observation. And we typically find, and also the bigger the planet, the bigger the dip in the light output as well. Right? If you just go up to here and compare, for example, Kepler 8b with Kepler 4b, they're called Kepler because that's the telescope that discovered them. You can see the drop in output. The period is the same, but the drop is much larger, right? So there's an inherent bias into what we're actually going to find based on how we're finding it. Question from Pedro. Is this how we detect the elements of the exoplanet via the light waves absorbed? Yes, that is how we wouldn't do that with Kepler or TESS. They're not, those space telescopes are not set up to do that. But you would do that with some of those large ground-based telescope arrays. They will look at the emission spectra of the star and see if there's basically absorption bands in that emission spectra when that planet transits in front of the star. Yeah, so that's what we'll talk about a little bit more on Monday. When we look into like particular exoplanets, like how do they actually figure out that this is a water planet, for example, or this planet has certain atmospheric composition or whatever. So yeah, that's exactly how we would do that. There's also reflected light as well. So you can actually look at planets, and as long as they're not too close to their sun, you can kind of like block it out, right, with a hand in front of your eye. You can actually look at the reflected light from planets too and see what wavelengths are absorbed by the planet, which ones are reflected back out again. Yeah, so it's kind of mind-boggling, to be honest, really. You know, these things, particularly the Kepler targets, are they're around on average, I think, about 400 or 500 light years away, which is pretty nuts. You know, this is it's a distance that you can't comprehend, I don't think. You know, if you're traveling at the speed of light, it would take you 400 to 500 years to get there, right? And you'd also have infinite mass as well, because that's what general relativity and stuff. What was I thinking? Yeah, that thought just fell out of my head. It'll probably pop back in again. We're not going to talk about that. You can look at it if you want. I kind of understand it, maybe. But I forgot to take it out, so don't worry about that too much. You can also find exoplanets directly just by looking at them. This is astonishingly hard because essentially planets don't reflect a lot of light, and if the way they reflect more light is being either larger or closer to the star, and if they're too close, then you'll never see it because they're essentially um, blocked out by the amount of light coming from that star. And so there are very few planets that are found by direct imaging, but once we know that the planet is there via other methods, then we can try and direct image it via using a different telescope, particularly in infrared as well, because they reflect better in infrared, obviously, than they do in the visible spectrum. And so this is I think this was one of the first ones detected by direct imaging. But you can see here in that tiny little dot just there where it says 2012 is what we think is a planet orbiting this system. And it's kind of I think it's a protoplanetary nebula. I think there's actually read about another one that's the same. So it's still in the process of forming a solar system. And this black thing in the center is called, I think it's coronagraph. It's kind of funny, actually, given current situation. It's got nothing to do with either beer or viruses. It's just a shield that's kind of placed in front of the detector so that the light of the star doesn't bleach it out, basically, so you can see fainter things. Actually, if you look at a lot of pictures of our sun, and you'll see that that's used, so you can see the cool stuff around the other side. And then this is really trippy. So here, I don't know how well I'll do in explaining this. You can also have what's called gravitational microlensing. And so I'll do my best, right? Basically, due to curvatures in space-time created by, let's say, here's us on Earth. There's a large, massive object between us and something behind it that we want to look at. That massive object, let's say it's another galaxy, right, will bend the light of that object so that light won't come straight to us. That light will kind of curve around, and we'll observe it as coming from different directions, even though it's coming from a single point source. See, I told you that's kind of crazy to think about. Don't ask any questions. That was a joke. You can ask questions if you want. I just might not be able to answer them. And so this here is an example of gravitational lensing, right? So essentially there's a galaxy behind this galaxy here, but this one is sufficiently massive that the light from the galaxy behind it gets bent like in a sheet and arrives at us in what looks like an arc shape, right? And so that's gravitational lensing. It's basically curving space-time so the light follows a curved route to us, kind of around something. I told you it was trippy. Yeah. So amazingly, go on, Jim.
Kind of like refraction. So kind of like refraction for light through like a glass or lens, but it's curved instead of just angled.
Yeah, exactly. So it's it doesn't just scatter it out. It's almost like you know,
Maybe
the way
gravity from the other system bends the light at the arc, and that's why it comes to us like that.
Correct. Yeah, because essentially light from another system is going to be radiating out in kind of like spokes, right? It's going to be from a point source. And so that light coming out then gets bent back. So we're not seeing just the single ray of light essentially that's coming straight from that point source to our eyes. We're also seeing the other rays of light which were heading out, you know, to either side of us, then get bent back. And so that makes it look like an arc shape. So I often think of this more in terms of like flat surfaces with like a marble dropped in, you know, like the gravity well kind of thing of, you know, what gravity is, right? You know, why we have big powered rockets to get out of Earth's gravity. And so essentially there's a kind of like a dip in that fabric, right? That, four-dimensional space, I guess. And the light is going out, kind of runs around the rim like it's like in a skateboard park essentially, and then it comes out on the other side at a different angle. That's another way of thinking about it. Not sure that's very helpful, but it's kind of how I think about gravity.
Yeah, totally makes sense. For real.
Okay. I'm happy whether you're serious or not, but anyway, the crazy thing about that is that if there's basically you would use that source light as a basically like a light source to be able to detect things moving in front of it. And so if you have a star moving in front of that light source, you will get a basically a peak in brightness, right? Because there's more light being curved from that original source to you, and so it will look kind of bright, it will look lensed. So you'll actually get a duplication, which you can see here in the middle. Now, if there's also a planet around that star, you'll get a duplication of that image on the left-hand side. And then as it transits, it will then cause that duplication to travel to the other side until that star kind of passes in front of that light source. Or if it's permanently there, if you're just lucky that those two things align, pardon me, you'll see this periodic changing in the lensing due to the added mass, essentially, of that planet adding to the mass of the gravitational mass of that star to cause that lensing to change a little bit. We haven't found very many by gravitational microlensing. It's pretty difficult to do, because not only do you have to have everything just so for the planet and the lens star, you also have to have something sufficient like light source behind it, and so there aren't a huge number of those situations cropping up. Okay, so we touched on it ever so briefly, but just to go back to this, right? This is kind of an extension of these diagrams, but essentially you can see the inherent biases in terms of what kind of exoplanets we discover, right? And so there's a huge bias to really large things, like Jupiter's. There's actually what we call there's a new category of planets that we call hot Jupiters, right? And so these are, because we always thought, Jupiter, gas giant, far away from the planet, right? It's going to be cold. But we've found a huge number of really large Jupiter-sized planets really close to their star. Literally an orbital period, get this, of, a matter of days. But you can see the bias here that most of the exoplanets found are large, and we would be, we're about 1/300th of the mass of Jupiter. So we would be kind of down here around the 0.01 level. This is around Earth, kind of down here at the bottom. And so the vast majority of planets found are both more massive than Earth, and also typically are much closer to their planets than Earth as well. And here are the odd other ones that are found by like direct imaging or microlensing. Is there even one on there? Yeah, there you go. There's a few on here by microlensing. Not a huge number. So however many we've found, looking at that one tiny part of the sky, is going to be a massive undercount. And there are almost certainly an awful lot more Earth-sized planets out there. We just haven't been able to see them yet. I think that's probably enough astrophysics for one day. Sorry, my dog's licking my foot. I don't know why. You see?
Attention.
I think she's missing some essential ingredient from her diet that she can only find on the bottom.
She's gathering the fungus.
That's right. Or some kind of salt or something like that. I don't know what. Anyway, so that's quite a lot to take in one go. And there's a lot of information in here. So have a think about that. If you have any questions over the weekend, just email me or bring them to class on Monday. And then on Monday, we're actually going to start looking at some of the candidates that we have found, particularly ones that we have more information for, like say about, sorry, it's really distracting having your dog licking your foot, particularly at information about atmospheres and stuff like that. Now she's licking the other one. Saves me having to have a shower, I guess. Just start doing my legs and things. Yeah, and then we'll just, so NASA has some like super cool animations of solar systems and things like that. So we'll look at a few of those on Monday. It's really cool. Anyway, that's pretty much it from me. Does anybody have any questions?
No, sir. Appreciate you as always.
Likewise. All right, cool beans, everybody. I shall have a great weekend and sorry. And I'll see you on Monday.
Yes, sir. You too.
You too. Dog, seriously.